Hi, I'm Ryan Nickel, CTO at DSA Ocean, and today we're going to talk about using radiation and diffraction data of ship hydrodynamics calculated on a different computer in your seakeeping and maneuvering project. So why would you want to do this, and what's this all about? Well, the radiation and diffraction calculation process can take a few hours. It depends on the details of the mesh and the project. It can be a little resource intensive on CPU and RAM usage, so it's kind of nice to be able to offload it onto a different computer while you work on other things. And I just wanted to highlight a few things to watch out for when copying that information into a project on a different computer. So for this, we're going to use the generic offshore supply vessel sample project you can download off our website. And this is a little bit different because we have a heavy ship and a light ship configuration. That just means two different displacements, both of which, when you change the displacement, you have to recalculate the hydrodynamics. Oh, and by the way, the vessel data that the generic offshore supply vessel is based on is provided by provided by Fleet Zero, so I just wanted to say a big thank you to them for that. Looking at the heavy ship sample project here, what's different about this is that you'll see a rad diff out file, which is a text file with the summary of the output of the calculation process. And there's some details about that we'll look at more closely later, as well as just showing the computation time. It takes a few hours to go through this. And the raddiff.db.bin file, which has all of the data that's loaded and used exclusively by the ShipMo3D toolset program. So the other projects don't have this at the moment, but it's something that you can play around with and get a feel for working with this. So what we'll do is we'll open ShipMo3D toolset here. We're going to open the heavy ship configuration. So we'll go open, navigating to this folder here. There's the project. Just like all the other sample projects, you'll need to go through adding the existing data. And of course, noting that draft at midships and is configured for the heavy ship condition. Note the height of CG from baseline. This is going to be based on some value for the configuration in that system. In this example, this is going to be related to something close to the maximum allowable kg above baseline, CG above baseline for that configuration. Of course, it's going to be specific to your project. But we'll go add existing data, panel hull, and of course we've got a panel hull configuration there already. Make sure that it's pointing to information on your computer. The hull variable mesh is already provided, and we'll have to save and run that. Nothing else is provided otherwise. So when we view the mesh distribution, you can see here, this is a simplified kind of version. It's a little bit optimized for calculation speed with a bit of a coarser mesh in the middle. It's kind of nice to see. I like the wet hull in yellow and dry hull with ship parts view is kind of nice. And just to get a view of that. Next we have panel lid, just like all the other projects. And panel lid, of course, being very helpful at reducing any irregular frequencies. So the wet hull file that we just generated in panel hull, we have to include that. All the calculation processes go through with this. So there's our lid inside the hull that suppresses any irregular frequencies. Perfect. Now here's where things get a little bit different. We're adding existing data. We're adding the rad diff file. Now the difference here is, yes, we have the wet panel hull and the wet panel lid. These would be the same that we've used to compute it already. But the thing is, we don't need to actually run the calculation because the .out file was included. So you don't click run. You can actually see the output file here. Now this is just a copy of the text file we opened a moment ago with all the results already computed. And you can also plot the radiation and wave radiation, damping and added mass values for surge, sway, and so on, and get an idea of what all those look like. So normally if you click run for this particular set of configurations, it's going to take a few hours to go through, but you can skip that step because there's a database file provided. So you would go to the next step and build ship, where you assemble the final details of the ship model and appendages and everything. So here's the hull. This is the radiation and diffraction database file that's in this case it's included with it, and this may be the file that you compute on a different machine and copy it in here. So this is how it gets incorporated here, but you can, if you have the .out file, you can also do plots and get some idea about what's going on with the ship model. There we go. So if we look at the other details of the configuration of the offshore supply vessel, you see that we have rudder, propellers, and bilge keels added as well. So we'll save and run this, and then we can plot the ship with appendages in build ship, and there's the whole ship model ready to go. If you like, there's also an existing Seakeeper random configuration. I mean, this is really easy to change with the C state. So it's asking for here, where's the ship model that you put together in build ship to run the analysis with. So we're pointing it to that file. And I mean, it's really easy to change the speeds and the C state conditions you want to be looking at here. And the actual calculation of the ship performance in that C state, takes only 2 seconds to do. And of course, you can see the roll RMS and lots of different forward speeds and whatnot as a result of that. So that saves a lot of time in working with process data. Here's the thing that you really got to be careful about in looking at this. You need to make sure that you're keeping an eye on the displacement, the draft at midships, and the height of kg. And you'll see that in the output here. If you go view output, I've already got it open here in the tab. It copies it in the output of the calculation process. Here's the draft in midships 4.2 and the height of CG above baseline 5.8, 4.2, and 5.8. Those are the same. That's great. So we're not mixing up we really don't want to mix up the radiation and diffraction database file because it could have vastly different numbers in it, as it would with the lightship configuration, which has different hydrodynamics with a different displacement, a different footprint in the water. The data is saved with respect to the CG location in this the database file that's calculated here in the ShipMo3D toolset. So if you want to change the CG, you got to be careful. You will need to go through the process of updating that in all of the applications here and recalculating it. So at the end of the day, if you're unsure about if you're just not sure about which displacement it is calculated about, do be careful. Just rerun it, and yeah, it's a one-time calculation for that displacement for that CG value. But once you have that done, that one-time calculation done, you go into here into Seakeeper random. You can evaluate all kinds of ship performance. You can change the appendages, update the radius of gyration as well, and then reevaluate the dynamics pretty much instantly. So yeah, I just wanted to show what it would look like putting together a ship model when you are using a radiation and diffraction database computed on a different computer, and what that would look like and what to watch out for. So thanks for watching.